Alright, yeah, that's working. That's working good. That's working really good. Okay. Sorry about that. Little update to software caused images to be weird, and so I had to fix the images. But there we are. Alright, we are in the very, very last section of the book called Dividing Polynomials. In general, this is going to be the last lecture. I will meet on Monday. Classes end May 11th. What is Monday? Monday is the 11th, so I will meet, answer any questions people have. We can do that as a Zoom meeting. We can do it in this format. I'll do any examples that people want, but there won't be any formal presentation of material. That said, if you need anything, please email me. Email's a little sporadic from everyone. Sorry, I had the software problem, didn't do my normal introductions. Alright, that said, we're gonna work on this last stuff. It shouldn't be too long. There's a couple weirdnesses in dividing polynomials. But what we want to do is look at one particular thing that comes out of it more than anything else. Yay! Things are working. Wow, that reboot worked really well. Our idea is we were able to take two binomials and using the firsts we get x squared, and then in my outers I have positive 2x and minus 3x minus 6, and being aware that these middle terms would come together, we could get a trinomial in this form. And these trinomials, especially when you have a power of 2, power of 1, and then a constant, they're called quadratics. And most other studies of mathematics do a large focus on quadratics. Okay, we're introducing you how to get to them here. What I want to hope we can do is how do we break them apart? How do we tear them down? And since we're looking at the reverse of multiplication, we're going to look at division. You don't see what I'm writing. Did it do it again? Oh man. Alright, I was so happy it started working. Let me see if it comes back now. Did that update? Did that change? It changed on my end here. Let me see on this end. Let's see here. Let's see. I have a little time delay from you here. There, it changed there. Let's see if I can see it continue. Does this still work? I'll come over here and see if it's doing it there. The time delays are a little odd. I apologize for those. No, the cursor doesn't appear to be moving. Does it? Oh, wait. Maybe. I'm watching on the interwebs with you. That's how I make sure things move through. Just these time delays are a little odd. I'll clear the head and I'll restart after this. Trim it off. Oh, I saw the cursor move. But do I see any more writing? No. What is happening here? Wow! It does it in bursts. All right. Well, that's fucked. Hey, we'll do this. Bear with me here. See if that flips over. I apologize for everyone here. It's definitely having some issues. I thought I fixed it because it was starting to show screens, but it's refreshing the screens very slowly. So hopefully, yeah, good. All right, this is gonna work. Not ideal, but we'll get there. All right. This is gonna be odd for me because I see what I need to see over there, but you're over there. And so I'll tend to talk to you like this. I should be talking to you like this. And I definitely did not wear the proper t-shirt for today. This was, kicking around the house bit. Not on the interwebs thing, so. All right. I'm double checking to make sure that goes through, and then I'll come back. Yeah, that's coming through. All right. All right. I apologize for things being things, but luckily I have ways to adapt. All right. So I will repeat ourselves. I'll repeat myself and make sure what I'm writing is appearing. We looked at multiplication. I'm going to try to get my cord from banging here. We looked at multiplication as being a thing that worked on taking two binomials and we get a trinomial. And we had our firsts, so we used the FOIL idea. Firsts times the first is x squared. Outers, my outer, negative 3 times x is negative 3x. My inner, negative 2 times x is negative 2x. And my last, negative 2 times negative 3 is positive 6. And we get these middle terms that would combine. Whoops. And we get this nice trinomial. It has a power of 2 in x, a power of 1 in x, and a constant. This is called a quadratic. And they're important functions. This standing in front of the camera thing, don't like. I should have shaved, right? Sorry. These are called quadratics. And quadratics are very important. They eventually continue with your mathematics. You'll see they'll make shapes like this versus linears, which make shapes like this. Quadratics have minimums or maximums in that shape. And so they get used a lot in our models of things that are not quite linear. But what we want to do is what we've always done, which is once we learn something, we want to reverse. These processes can be reversed. If I add, I can subtract. If I can multiply, I can divide. And so for today, we're going to look at the division and how we divide out larger polynomials. We're going to do the same thing we did with polynomials. We started by focusing on the monomials because the monomials built the parts. So we're going to work on that. And overall, this whole thing ends up getting called factoring. I'm sorry, this isn't a large board. I'm going to be erasing a lot, and that might slow things down. I do apologize for that. So, in general, this idea is called factoring. polynomials. And our first focus will be on mononomial parts. Mononomial parts. So, I can have a monomial and I'm going to divide it by another monomial. And this is telling me that I have negative 12n to the 6th divided by 3n. Now, in this format, a lot of things are not apparent for us. So in this case, writing it in the fractional form of division can help us. Now remember, these symbols are interchangeable, I hope. Right, we have the ratio symbol, 6 to 2 is the same as 6 divided by 2. And this crazy symbol ended up being the fractional bar and the ratio symbol put together. And so when we see divisions, sometimes the form that brings us the most utility. This means the same as this. But in fractional form, we can treat it like a fraction. And we go, hey, you know what? 3 goes into 12. We can focus on just the numbers. Just the numbers. And just the variables. We can look at them as separate things. Because they have slightly different rules that would define them. So I could even mentally give them a little space here. Right, at least 6 feet in between them. All right, so the number part gives me negative 4. And the variable part, well, I have my rules of exponents. And our rules of exponents are saying I'm multiplying this 6 times and I'm dividing one of those out. We kind of used it as I have some power upstairs, the same base, and some power downstairs. I subtract the powers. Yeah, M minus N. Tried to, this was actually hanging here, so when I put the camera on, I could see that I was fitting everything in. I know that it has a wooden boundary. I don't think well. So I have 6 here. Remember, this is n to the 1. We never talk about the first power. So my n is 6 minus 1, or n to the 5th. And so when we process these monomials, we kind of count how many times we're multiplying our variable, and we subtract the upper power. We subtract from the upper power the lower power. And so we get into the 5th. And so monomial division, it's line all the variables over each other and use this rule of division for exponents. Take the constants out front and treat them as a number. And so we get minus 4 n to the 5th. Well, with all divisions, we can double check to make sure we did it right. We can take our answer and multiply it by our divisor. 3 times negative 4, right at the bottom there. Ooh, I'm just going to make it negative 12. Yeah. And n to the 5th times n to the 1st. I add my exponents, n to the 6th. And it checked. So we have the ability. Glad you guys like the t-shirt. I did not plan this. This is what happens with a technical glitch, right? At least I dressed today. I'd be running for a robe. Oh, I don't own a robe. We'd be screwed. So at least our division checks, and it does what it says on the tin. I'm gonna do another one here, slightly uglier, because I got one variable in my polynomial. I'll look at a polynomial with a couple variables squished together. Notice the monomials, there's no additions or subtractions yet. They're going to make things a little weird for us when we do additions and subtractions. I'm running low on yellow. I think I will try traditional white. I got the Groucho Marx size thing. All my good chalks are at the college. All my good chalks. This is Crayola sidewalk chalk, which actually is an amazingly good chalk. I'm quite impressed by its quality. It's very similar to railroad chalk, which comes off of most everything, which means it writes nicely. And it's big, it's chunky, so it's easy to write big, forces you to write big. Alright, I'm going to write a really ugly division here. Give me a second. So I have done something where I get 20 p cubed q squared r to the fourth. However those variables are coming together for me, that's the expression I'm going to use. And I'm going to divide it by -5 p squared q squared r. It's ugly. Alright, a lot of stuff going on. That's usually when I mean ugly, there's a lot of things going on. It's a nice thing, at least I'm hoping we can appreciate the nice thing from all this, is that the rules we use build these ugly things. And so we can usually find a toehold in to make them less ugly. So for me, it's going to be, I'm going to write this in fractional form. I know. I told you this was ugly and I was going to try to improve it, and we all hate fractions. It's okay though. With a fraction, it's really okay. I have now lined up like for like. Just like when we like adding up and down, because we line up things that have the same place values, I can line up things that have the same variable values. And I've isolated my numbers to the front. So 20 divided by -5 is -4. I'm multiplying 3 p's upstairs. I'm dividing that by 2 p's. 3 p's and 2 p's, please. So 3 minus 2 leaves me with 1 multiplication of the p. I have q squared divided by q squared. Well, anything divided by itself is 1. So we could say they cancel, or q squared divided by q squared is 1, or I'm multiplying 2 q's upstairs and I take away from a q 2 multiplications, which leaves me with none, and anything to the 0 power is 1. I have a tendency, because it now comes up so much in mathematics, that whenever I see the exact same thing over itself, it becomes 1. This is just weird. This whole thing, I don't like being on camera. And now I see me over there, all puffy hair and unshaven and ugly t-shirt on. Damn technology breaking. But same thing over itself is 1. Well, when we multiply by 1, we don't write it, right? Because anything times 1 is itself. So I guess a good mentality is the q's cancel. Then I have r multiplied 4 times divided by 1, so I'm going to get rid of one of those, and I'll have r cubed. And that gives me my answer. So monomial division, I personally think whatever form you get it in, putting it into a fractional form, and then putting like for like over top of each other, helps you sort out what you need to do. The key is the things that have powers, we subtract. The upstairs loses what's on the downstairs. The upstairs loses what's on the downstairs. The upstairs loses 3 minus 2. I'm only multiplying by 1p. I know they're not writing ones, you know. It's a tradition. It's a crazy tradition. We'll get there. All right. Well, I've divided one polynomial by another polynomial. I'm going to have to chunk this up for us. We're going to make our division a little bit weirder. And the thing I'm going to focus on is this first part. I'm going to make it a polynomial. I'm going to let this have additions and subtractions. It's okay. It's going to look ugly, but we'll break it into simple things. Factoring doesn't consider like terms. No. Factoring looks for the same variable, but not. So Janine asked a really good question. She says, so factoring doesn't consider like terms as polynomials. Adding polynomials. So adding polynomials, 3x squared plus 4x plus 3x minus 1. Right? These powers can't come together. X times x and just x on its own, I don't have a method of adding them. Unless I knew exactly what x was. So we collected like terms. So the things that had the same power of x would come together. Whoops, that's x to the first. So I'd have 7x there. The addition and subtraction gathering like terms pulls them together. But when I'm dividing or multiplying, because under the hood, and I'm just going to use the P3 as an example. Under the hood, P3, P to the third power, divided by P squared. Well, this meant that I was multiplying P 3 times. And this meant I was multiplying P 2 times. Same thing over itself, that becomes a 1, so that goes away. Same thing over itself, so that becomes a 1. And I'm left with just a lowly P there. So what it means to take something to the third power and having it itself underneath it is different than what it means when adding. So we applied this slightly differently. And your question was exactly right, Janine. It was the right idea. These powers, when we're multiplying, can come together or subtract, because what it means to multiply is to put these things together. And instead of having to write this out every time, like I don't want to write 3 P's, 2 Q's, and 4 R's upstairs, and 2 P's and 2 Q's, and an R downstairs, we find the rule that when we are multiplying powers or dividing powers, we can add or subtract the exponents. All right. Let's extend this further, because I think the next thing we're going to do actually kind of looks around the thing Janine just asked about. I will put this here just because of where the questions are coming from. addition and subtraction, multiplication, division, exponents are powers, and the roots and parentheses. Multiplication was multiple additions. Exponents are multiple multiplications. And so when we look at these things, the rules usually involve doing something with the thing lower each time. But if we're doing powers and additions, they are separated from each other by multiplication as the operation. So it's actually powers and addition we can't do, but we can go the next level down. We built these things to represent each other. So if I'm saying 3x, I'm saying I'm adding x 3 times. When I say x to the third power, I'm saying I multiply x 3 times. And I just made it on the board. I've got like an inch of space here because of how close the camera is. I haven't put it out. The kids want to get a green screen so I can teach from like the middle of space or something. Yeah. So my reference for a kind of around the question Janine asked is the reason adding and subtraction with powers doesn't bring things together is because this is in the middle of them, right? These two things are linked, but these two things are not directly linked because we made multiplication out of multiple additions and we made powers out of multiple multiplications. And so there's kind of a filter you have to get through to get to the other. And we're kind of learning that filtering rule. And it's not mathematically, like a precise definition, but we built these things. We as human beings built these notations out of the thing below. And so when we're up all the way in these lofty heights of the powers, the things that work the easiest for us are the multiplications. The additions don't. Especially with the variables. Let's look at one here. Let's look at a polynomial divided by a monomial. So which one do I want? Now I'm going to move some stuff around. That should work. Yeah, my fat butt's not in the camera. Good. So 21x cubed minus 14x squared. That's my polynomial. And I'm going to divide it by 7x. Alright, so I'm going to actually do this in fractional form to help show you what's going on. I love being partially off camera. It's a floating arm. Alright, so 21x cubed minus 14x squared over 7x. So I write this as a fraction. Now here we're going to rely on something to help. And this only works if the addition and subtraction is upstairs. Right? I can have additions and subtractions downstairs, but I can't break them apart. I can break this apart. And here's why. When I had a common denominator, I could bring the numerators together. But it was only upstairs. This only worked upstairs. So, I can go backwards. Anything I can do for it, I can go backwards. So if I start here, I have some addition or subtraction upstairs, I can break it into 2 parts. Or 3 parts, or 4 parts, or how many parts are in this polynomial. So, I break it apart. I'm breaking it apart. I'm reversing what we would have done with a common denominator. Convince yourself. If you were to see this, it has the same denominator, which means you can bring the numerator together over the same denominator. That takes you back up to here. We need just a little space here. Well, this is a monomial divided by a monomial. So you have 21 divided by 7, that's 3. I have 3 multiplications of x upstairs and 1 downstairs, so 3 minus 1 is x squared. That gives me my first term. I have a minus sign. 14 divided by 7 is 2. I have 2x upstairs and 1 downstairs, so 2 minus 1 is 1. And then get this. We're able to take the addition and subtraction, and because of the division, we can do it term by term, if we do it in fractional form. Now, some people don't look at it as fractional form, so I take the whole thing and look at it kind of as like a reverse distribution also. So I'm trying to keep the same thing we did with monomials. I wrote the whole division in fractional form, and then I said, hey, I can break it apart. Well, some people don't do that, so we'll change that. There's where I'm at with that. Let me show you the other way of thinking about it. Now again, this is a monomial. There's no addition or subtraction into this. We'll have to do something different if there's an addition and subtraction in here. So what people will do is they'll say, well, I'm dividing this, so I'm dividing each term by the 7x. What they're really relying on is our definition of division, right? They're saying, hey, I could think of this as multiplying by 1 over this. And if I multiply by something in parentheses, I can distribute. So you can distribute the division through. Even when we were meeting in class, I don't care which way you do things, as long as they're mathematically consistent. I know now that we're doing this electronic homework and electronic stuff, I'm not going to see the way you're doing it, but I want you to find the one you see, the one you can latch onto and grab. That's usually helpful. But mathematically, they're the same thing. They're the same end results. They're just the steps you do to keep track of where you are. So 21 divided by 7 is 3. X cubed divided by x is x squared. 14 divided by 7 is 2. X 2 minus the 1 gives me a little x. And I got the same thing. I'm going to do another division by a monomial here. I'm really sorry about the loss of the electronic board and the little awkwardness of this. I hate being awkward because it's my natural state. I'm going to do a longer one. Negative 5a to the 7th, negative 5a to the 7th, b to the 6th, plus a squared, that is an a, trust me on it, b to the 4th, minus 15ab cubed, all divided by 5ab cubed. All right, let me read out my scribblings. Negative 5a to the 7th power. The 7th definitely clearer. B to the 6th power plus a squared b to the 4th minus 15ab cubed. Everything is going to be divided by 5ab cubed. It'd make me look pretty. I can stand next to it. Look, I'm prettier. Which is a long shot, right? So, I want to shave. So we can create this. Notice we have different terms with the division. So to simplify this, to start making it manageable, I'm going to take each term over the denominator. I'm going to make sure that each term gets divided by the denominator. So negative 5a to the 7th b6th, the first term, divided by 5ab cubed, plus signs of plus a squared b to the 4th, divided by 5ab cubed, minus 15ab cubed, divided by 5ab cubed. I hope verbally, you're here on this last one, ab cubed divided by ab cubed, you're hearing same over same, same over same. That should help us think, hey, we're going to get some cancellation here. Again, focusing on term by term, 5 divided by 5 is 1. So again, negative sign out front. 7 divided by a to the 7th, divided by a to the 1st. So 7 minus 1 is a to the 6th. B to the 6th, divided by b cubed. 6 minus 3 is b cubed. My numbers, well, I have an invisible 1 here. So 1 divided by 5 is 1/5. So we'll just write the 1/5 out in front. A squared divided by a to the 1st. 2 minus 1 is 1. Nice A. B to the 4th divided by b cubed. 4 minus 3. B to the 1st. We don't write our 1s. You can if you want. $15 divided by 5 is 3. And for me here, because I've been doing this for a yonk's age and then some, exact same thing over exact same thing. I don't care if it's made over multiple parts. Anything that's exactly the same divided by itself is 1. So ab cubed divided by ab cubed is 1. Or I can look at it part by part. A divided by a is 1. B cubed divided by b cubed is 1. And 1 times 1 is 1. 1. Yeah, I'm going to have to move this camera back. It's like almost at my fingertips. Too close. And so this simplifies to this. Alright. It looks ugly. We're all going there, right? But what I want to appreciate is if this is something you had a formula for, and this you were dividing it by something else you had a formula for, and they had the same inputs. And this is why we do this. Then you can simplify it to this. Because otherwise you have to do this on your calculator, store that number, do this, and divide the two. Well, here, you just do these steps on your calculator. You're reducing the amount of work you have when you finally throw in an A and a B. A lot of these simplifications will help us chalk dust. Will help us find patterns. And those patterns we find are nice, but it also reduces the amount of work we have to do calculating the things we have. So there's a lot of utility for this. It has no meaning right now, right? I don't know what A and B are measuring. I don't know what we're throwing into A or B. I just know that I have one thing in A and B, and I'm dividing it by another thing in A and B. And this represents some quantity, some massive number But if I know A and B, I know its mass and or quantity, and this represents some quantity in A and B. If I know A and B, I know it. And so I could divide them. They are numbers. And this does happen in processing. Usually it's not as bad as this because we try, most things we use, we rarely get above fourth or fifth powers in everyday mathematics. But the point of why are we doing this? What does this mean? What is A and B? What is the answer? This is the answer. We're taking something that would be complicated for us to plug everything into, and we're making it slightly less complicated. I know in the back of our heads we're going, what's the number? What's the number? What's the answer? I just want you to appreciate this is the answer. It is the simplified form. And the thing I always held in my head when I was doing these, other than the fact that I have a weird obsession with finding patterns, and there are patterns in here that are neat, nice to find, and I do like finding them when I can, is that when I finally figure out what A and B are, and I need to get the answer to whatever this is a lot less work for me to do than doing all of this. All right, so that was a polynomial divided by a monomial. I'm going to do one other type of thing here, and I just need to get my notes here. And this is a polynomial by a polynomial. All right, so we've been chunking our little pieces through. This always stumbles people. I think we have one question on it on the final. So take with it as you may. You're in a much better place than a lot of human beings because you've reviewed division. A lot of people who have been doing division on calculators haven't had a review of division in a while, and they're lost at this. But I'm going to review division for a second here. I'm going to do 32 into like that. 2000. When doing long division, place value became important. What numbers were in particular places. And so we were able to think of this whole thing as sliding across the places that were available. And what was generally happening was, well, I was saying, this is my thousands place, and 32 doesn't divide by a number into thousands. But if I have 3,500s, then in 100 times 32 gives me 3,200. But we didn't say it like that. We used the place value to do the work for us. And so we said, well, can I divide 32 into 3? No. Okay, move over to the next thing. Can I divide it into 35? Yes, it goes in once. Then I did 1 times 32. I subtract, and I bring down the next place value. And now this technically is representing 330 because of its place value. And I'm asking how many 10s go into 330 if I'm dividing by 32, which will go once. 1 into 32, or 1 times 32, and it gives me 10, and I can't go into 10, so I get a 0, and I have a remainder of 10. Right. The place value did the work for us. A lot of people learn this once, never come back to it. And they might do okay in math, and they eventually hit this part in algebra that we're hitting right now, and they haven't reviewed this since the one time they did it, and they've been using a calculator until then to check themselves, and they never fully got this algorithm of place values. Well, place values become very important when dividing polynomials by other polynomials. Specifically, we're going to look at dividing a polynomial by a binomial. So I'm going to come over here. Yes, that was the dog shaking. She's looking at me like, why do you have all this stinky stuff? All right, so we're going to look at 3x cubed plus 7x squared plus 11x plus 5. That's my ugly polynomial. And I'm going to divide it by 3x plus 1. Fractions are not going to help me here. I have to get this idea of place value, and I have to apply it to the polynomials. Now, one of the things I said that I do with polynomials is I write the highest power of x first, and then I go down. And this order of x values are going to help us. The order of x values is really going to represent our place values. Sorry, checking to make sure that the feed's still going. So I'm going to rewrite this slightly to make it look like a long division. And I'm going to divide by 3x plus 1. I'm going to erase this up here so that I have room up above, just like we would in a long division. Now my place values are going to be these powers of x. The nice thing about doing it in a variable compared to a number is we don't have to think of all the multiples. The only thing we have to worry about are the leading terms. So for right now, we only have to worry about the first thing here and the first thing here. So 3x cubed divided by 3x. So I'll write the division of my leading terms. So I have this here and 3x. Well, the 3's cancel, and x cubed divided by x is x squared. So that's the thing I need. I need 1x squared. Well, what did I do when I was long dividing with my numbers? Once I got my thing into my place value, I multiplied it back through by what's here. So x squared times 3x is 3x cubed. Right, I add my powers and my numbers out front. And then x squared times 1 is x squared. So I'm doing the same thing I did in long division, but I'm doing it with a polynomial. I'll only ever be dealing with a monomial at a time here. Only be dealing with a monomial at a time here. So this binomial and this monomial come together and they give this. Well, the next thing is we subtract. Now, for me to subtract, I try to change my signs in some color or in something different. When I do it with pencil and paper and I write these things through, we're going through. So Janine's asking, I guess, for a point of where we're at. I am dividing this big long thing by this thing. We have plus signs in both of these. So these polynomials, we have to treat like a long division. The thing that's going to take place for place value for us are the powers of x. That's the thing we're going to focus on, is the powers of x. And so for the first power of x, this bit goes into it x squared times. So I'll write my x squared up here, and I'll multiply it back through. 9 doesn't go into here, but it goes into here 6 times. I write the 6 up here, and I multiply it back through. Then I subtract. 3x goes into this x squared times. I multiply it back through. It's the same thing we do with numbers, but we're doing it with the variables. Our saving grace is here. We let the place value of the numbers drive it. Here we're letting the powers of the variable drive it. And the only simplification we get is all we have to worry about is the leading terms. Well, let's do this subtraction here. 3x cubed minus 3x cubed is 0. This first thing should always cancel, because that's what we're using to determine what value to get here. So 7x squared minus 1x squared is 6x squared. And I'm going to pull down my next value. Yes, we're solving term by term, and think of it like place value. So Janine goes, you're just solving term by term. And yes, we're thinking of specifically the terms of the things under here to be divided. They're all getting divided by, and we're focusing on the leading term here. But each power holds a place. And so we're saying, hey, how many times does this go into this first thing? Well, it goes in x squared times. Okay, we have x squared times, multiply this whole thing by x squared, subtract. Hey, this is what we have left over. And so we got to go, how many times, this is now my new leading term. And so how many times does 3x go into 6x squared? Well, 6 divided by 3 is 2, and x squared divided by x is x. So it goes in a positive 2x times. So now I need to multiply this 2x back through this. So 2x times 3x is 6x squared. 2x times 1 is positive 2x. I subtract. If I've done my job right, these first two things should go away, because these two things should be exactly the same. So I'm going to subtract, they go away. 11x and 2x gives me 9x. Did I miswrite this? And then I bring down my 5. Again, I have a new leading term. It's 9x. That's still my leading term there. Well, 9x divided by 3x. I keep writing. If you ever see me do these on paper, I kind of have these going down the side. 9x divided by 3x. The x's cancel. I just get lowly old 3. So 3 times 3x is 9x. And 3 times 1 is 3. I'll subtract. And I get 2. It's just, wait, there's a 2 there. I'm going to try to tilt it back. There's a 2. There's a 2. See? There's a 2. As a remainder. So I'll bring my 2 up here as a remainder. Now, I'm going to do it the way I showed you guys to do remainders. It's 2 over this. Again, we are just rewriting something to be in something that has less terms. This in general becomes very useful as you start getting polynomial things, because there are patterns that happen for square things and things to the first power that aren't obvious in things cubed. And so we try to break it into pieces. And this would be one piece, and this would be the other piece. And so there's patterns that come out of these things. They're breaking apart. In 126 and 162, you have to do a lot of this, and so the technique's there. I just want you to appreciate that the algorithm that does this is the same as what long division we did with numbers. And that's the last thing we need to know for right now. That gets us through what we did. This, I'm not going to stress, right? I want you to try the ones on the homework, try the ones on the worksheet, right? As you progress, if you move down the road for these, you will get loads of these in your polynomial sections. I just want you to know you have an advantage over most people, because very few people go back and review the algorithm for long division like we did. And so you have a process here that you can start. Now would be a good time to practice it, and I think it would come through good. All right, I'm done. We have practice worksheets. I've given you the worksheets. Everything is up on Pearson. If you have any problems with due dates or anything, please email me. I'm going to start sending some emails out tonight, tidying up. We technically have class Wednesday, or not Wednesday. Today's Wednesday. Monday. And Monday's class would have been the exam, the final exam, but I'll be available a whole normal class time. If anyone wants to Zoom, email, or if you guys email me examples of things you have questions, I'll put up. I have a set of examples Janine sent me that I am recording, which it looks like I'll be doing on the blackboard right now. So practice this. All right, focus a little bit more on the other divisions, the monomial division, monomial by monomial, monomial into polynomial. This polynomial and the polynomial really relies on that underneath the hood. But this should be the last thing in the groupings that you do. All right. I think I'm going to go put my head in a bucket of water and try to smooth out my hair.